Hello viewers, today we'll be looking at one factor experiment which is known as one-way ANOVA with unequal observation. In this case, we are looking for, we are testing for the difference of mean with unequal observation. So, one factor experiment with unequal numbers of observation is what we'll be looking at, and that is also called what? One-way ANOVA for unequal observation. So the first thing we are going to look at is to look at the table. That is an ANOVA table. How does a table look like, and how do we go about it starting from the table? Alright, so we're going to have this kind of table here. You can see we have 4 columns. In the first column here we have observation, we have variation. So the first here we have variation between treatments, or say between treatment variation, and this is the formula we are going to use to get the variation between treatment. So followed by variation within treatment, and this is gotten when we subtract the total variation. This is the total variation from the variation between the treatment. That will give us the variation within treatment. Alright, and the total variation, this is the formula we are going to use to get the total variation. Under the example, we are going to explain this better so that we'll be able to handle problems that has to do with one-way analysis of variance with unequal observation. And in the second column here, we have the degree of freedom. The first box here, we have A minus 1. This A stands for the number of group we are testing. The number of group we are testing minus 1 gives us the degree of freedom between treatment. Then here we have N, and this N is the number of observation. That is the total number of observation. So when you subtract the number of group minus the total number of observation, that will give us the degree of freedom within treatment. And finally, we have a degree of freedom that has to do with total. That is N minus 1, total number of observation, minus 1 give us the degree of freedom for total. Now in the next box here we have mean square, although this is called sum of square. So for the first treatment we have sum of square regression, and within treatment this is called sum of square error. Then we have the sum of square total. Now here we are dealing with mean square. So the first box here we have a mean square for between treatment, and how do we get this? Whatever we get in this box here divided by the degree of freedom here give us the mean square between treatment, otherwise called the mean square of regression. Now the other one here, which is an S cap subscript W square, and that is a mean square within treatment. And how do we get that? Whatever value we get here divided by the degree of freedom for within treatment, that will give us this. Now the last column is the F statistics, and that is the purpose of all this table. That is purpose of all this table is the F statistic that we want to get. And how do we get the value? So this is getting when we say the mean square error between treatment divided by the mean square error within treatment. That will give us our F statistics. That is a mean square regression divided by the mean square error give us our F statistic with degree of freedom within treatment and degree of freedom within treatment give us the F statistics. Alright, let's look at examples. So using the following data, perform a one-way analysis of variance and using alpha equals to 0.05. This alpha equals to 0.05 is our level of significance. Now this is the table. From this table now we can see that here we have a 3 group, which is a X, Y, and Z. So we have 3 group, and under the first group, which is X, we have a 1, 2, 3, 4. That is a 4 number of observation. For group 2, we have 1, 2, 3, 4, 5. We have a 5 number of observation. And for the last group, which is Z, we have just 3 number of observation. We can see, and this is why we call it unequal number of observation. Now the first step here is to test the hypothesis. So when we test the hypothesis, and that is what we're going to work with. Now, step 1, we have an hypothesis testing. And what is our hypothesis here? We're going to test the H0 against the H1, which is a null hypothesis against the alternative hypothesis. So we have it as this. There is no difference among group mean. That is for the null hypothesis. That is, there is no difference among group mean. Among these 3 group mean, that means there is no difference among the mean of these 3 groups. Then versus the alternative hypothesis, which is a H1, there is difference among group mean. So what are we doing here? We are to accept or reject the null hypothesis. By the time we accept the null hypothesis, then we're going to reject the alternative hypothesis, which is H1. And if you reject H0, that means you are accepting H1. Now, the second step is a level of significance. What is our level of significance? You can see right from the question here, we are given 0.05 as our level of significance. So therefore, we have alpha equals to 0.05 as our level of significance. Going further, we talk about the step 3. And the step 3, we have it as the statistical tool we are going to use. Right from the video, we are using one-way ANOVA with unequal number of observation. So that's what we're going to use. Now, introducing the table again, we have this. This is the table we are testing. So before we move further, we need a total for each group here. We need total for each group, and that's what we're going to do here. So we have a total. We will add 3, 5, 4, 8. We add all together, and this will give us 20. Now for group 2, 5 plus 7 plus 3 plus 4 plus 6. We will add all this together. We are going to have a 25. And for the last group, which is Z, we'll add 3 plus 2 plus 4, and this will give us the total of 9. Now, we will add all this together now, 20 plus 25 plus 9, and that will give us the grand total, and that will give us a 54. We can see that. Alright, before we move on, the number of observations for each group is given as A equals to 3. A is the number of group. We have X, 1, 2, 3. So we have 3 groups here. N1 is the number of observations for the first group. And if you know, we have 1, 2, 3, 4. That is what we have for here. N2, the number of observations for group 2, we have 1, 2, 3, 4, 5. And that is what we have 5 here. And for Z, which is the third group, we have 3. And we have 1, 2, 3. That is 3 number of observation. Now, we can see that we have N here, and this N stands for the total number of observation for the whole group. If you add 4 plus 5 plus 3 together, we're going to have 12. It's just as counting each box here, each number here, each observation here. By the time we count the whole observation here, we're going to have 12. Alright? Now, in order to make things easier for us, there is something called correction factor. By the time we get our correction factor, that will make the whole thing easier for us. And how do we get our correction factor? We say correction factor C equals to T raised to the power 2 divided by N. That is the grand total number, the grand total, when we square the grand total divided by the total number of observation, will give us the correction factor. And if we do that, we're going to have 54 square over 12, and that will give us 2916 divided by 12. So by the time we divide this 2916 by 12, we are definitely going to have 243. So that is the correction factor, which we're going to use in the shortcut formula we're going to use in this video. Now, the first thing we are going to calculate here now is our total variation, just as we explained in the table, in the previous table. So the total variation, the formula is given as summation j dot k x raised to the power 2 minus c, and this c is our correction factor from here. So we already know the value of c, which is 243, and that is now the problem now is, how do we get this x squared, which is summation j dot k? How do we get this? And this is very easy. What we are doing it here is that each observation here, we're going to square it, then add everything together. What I'm saying that is 3 square plus 5 square plus 4 square plus 8 square plus 5 square. up to 4 square. We're going to add everything together, then we'll subtract it from this correction factor, and we're going to have a 3 raised to the power 2 plus 5 square plus 4 square plus 8 square plus 5 square, then definitely plus 4 square, then minus this is our correction factor, that is the square of each observation. The sum of square of each observation here is what will give us everything that we have here. Then we subtract it from the correction factor, and by the time we do this, we're going to have 278 minus 243. The whole of this give us 278 minus 243, and we should not forget it has to do with everything here. In order to save space, that's why we put this dot 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 here. So finally we have 783, 278 minus 243, and by the time we subtract this from each other, we're going to have 35. So it means the total variation for this table is 35. All right. We need to calculate the variation between the treatments. So, and the formula for that is given as variation between treatment, let me see, V subscript B equals to summation xj dot square divided by ng minus c. So this is the formula we're going to use here. And what does this x squared j squared? You can see the other time we calculate group total. So now each group total here divided by the number of observations that make up the total. That is what this one stands for. Now let's look at this. We're going to have, just like we say, n1 equals to 4, that is the number of observation under the first group is 4. n2 is 5, the number of observation for the second group is 5, and n3, that is the number of observation for the third group, is 3. Now the total for each group divided by corresponding number of observation. You can see the first total is 20. Then the second group total is 25, and the third group total is 9. So we're now going to square it divided by corresponding number, total number of observation here. So we have VB is equal to 20 square over 4 plus 25 square over 5 plus 9 square over 3 minus 243, which is our correction factor. You can see 20 raised to the power 2, that is total observation for group 1, that is a square of total observation for group 1 divided by the number that make up the total. 25 square over 5, the square of the total for the group 2 divided by the observation that make up the group 2, that is the number of observation that make up the group 2. And we also have for 3 here. So by the time we add all this together and we'll square and then add everything together, that was going to give us 252. So we have 252 minus 243. So by the time we subtract 252 from 243, VB is going to give us 9. So it means 9 is a value for variation between treatment. And we should not forget, the last one we need to calculate here is the variation within treatment. And the variation within treatment is given as, so variation within treatment, which is V subscript W equals to V minus VB. This V is the total variation. VB is the variation between treatment. And the last slide, the previous slide, we calculated the V, that is the total variation, and we got 35 for total variation. Then for V subscript D, this is what we have here, which is 9. So it means we are subtracting 39 from 35. So we have V subscript D equals to 35 minus 9, and that will give us 26. So we have 26 as a value for the variation within treatment. Now, that we already know the value for the variation between treatment, variation within treatment, and total variation. The next thing is to prepare our ANOVA table. So we have this now. You can see the first column is for variation. So variation between treatment, we have the value as 9 from this point. Variation within treatment, we have the value as 26, which is this. Then we have the total variation, which is 35. And if you add this 9 plus 26 together, we're going to have 35, although we got 35 from our calculation. Now, degree of freedom. Degree of freedom for the variation between treatment is given as A minus 1. And we should not forget that A stands for the number of group. And the number of group in our table is just 3 group, which is X, Y, Z. That is 3. So when you subtract 1 from 3, we're going to have 2. The total number of observation, that is total number of observation in each group, is 12. Then say 4 plus 5 plus 3 will give us that 12. So now say 12 minus A, which is 12 minus 3, give us 9. Now 12 minus 1 give us 11. And if you add these two together, 9 plus 2 will definitely give us 11. Now the next column is the mean square. The mean square for variation between treatment is gotten, that is, we say sum of square for variation between treatments divided by the degree of freedom here. That is the sum of square here divided by the corresponding degree of freedom here. 9 divided by 2 give us 4.5. The second row, we have 26 divided by 9 give us 2.87. So 4.5 is the mean square for variation between treatment, and 2.87 is the mean square for variation within treatment, otherwise called mean square error, and this one is also otherwise called mean square regression. And how do we get our F statistics here, which is our value of F? So 4.5 divided by 2.87. Use this to divide 2.87, that is 2.87, and this 4.5. 4.5 divided by 2.87 give us the 1.57, and that is our F statistics. So in taking decision and in making conclusion, we're going to use this F statistics here, F value here, compare with the F table, that is the F test from the distribution table. So whatever we're going to have, we're going to compare the two together. So in checking for the table, we are checking for degree of freedom 2,9. That is degree of freedom 2 and degree of freedom 9. That will give us the F statistic from the table. Alright. The next step now is the decision rule. So how do we make our decision? We said if the F calculated is less than F tabulated, we're going to accept the null hypothesis. If the F calculated here is what we have here as 1.57. If it is less than the F table, that is the F we're going to get under the table, and how do we get that? We're going to use the level of significance, which is 0.05, under the degree of freedom 1 and degree of freedom 2. And degree of freedom 1 here is 2. And the second degree of freedom here is 9. So we are picking for 2,9 under 0.05 level of significance. And by checking that on the table, F subscript 0.05, 2,9 from the table will give us 4.26. So we said F tab into bracket F of 0.05, 2,9 give us 4.26 from the table. Now we are comparing this F, which is 1.57, with this F, which is 4.26. And as we can see here, that our F calculated, which is 1.57, is less than the F tabulated here, 4.26. So before we conclude, all right, this is the A, we stand for 3, and we have N, we stand for 12. So before we conclude, let's check the table and see what we're talking about. We're checking for 0.05 under 2 under 9. So here, this is the table. We have the table here. All right. This is 0.05 level of significance figure. And for V1, which is the first degree of freedom, we have 2 as the value. We have 2. And for the second degree of freedom, we have 9. So where the 2 intersect is what we are targeting now. If you trace it from this table here, you trace it down and you trace this one down, we can see that the 2 meet at 4.26, which means the value of the table is 4.26, and that is what we discussed earlier. So from this point now, we can now take our conclusion. Say step 5, conclusion. What do we conclude about? We say, since the F calculated, which is 1.57, is less than F tabulated, which is 4.26, then the null hypothesis is accepted, and we concluded that there is no difference among group. We concluded that there is no difference among group mean. So which means that we accepted in H0, which is a null hypothesis, and we rejected the alternative hypothesis. And this is how to go about when we analysis of variance with unequal number of observation.